Now we're going to start looking at the properties of logarithms, which are useful for either taking several logarithms and combining them into a single log, or for taking one big complex logarithm and breaking it into several smaller, simpler ones. These are the properties that you should have seen in Algebra 2, although you might not recall them quite yet. The first one is the product rule, and the idea behind it is if you have two things being multiplied inside of a logarithm, then you can split it up into two different logarithms that are being added together. Notice that the base does not change, so if you have base 3, then the other two logarithms will still be base 3. All that's happening is we're taking one logarithm with a product of two terms, and we're making it into two logarithms separately that are being added together. Similarly, we have the quotient rule. So you can take two terms that are being divided and make that into separate logarithms which are being subtracted. And again, the base of the logarithms is not being changed in this case. The easiest way to remember these properties is to recognize that it's the same rules used for exponents. If you are multiplying something like x cubed times x squared, then you add the exponents. So remember, logarithms are exponents. That's why these rules match that. So when you multiply terms, add the exponents. When you are dividing terms, you subtract the exponents, and that's what this is showing. And then the last property is called the power rule. So if you ever see an exponent in a logarithm, you can actually take that power and bring it out in front of the expression. So in this case, you end up with p times, and then the rest of the logarithm doesn't change. It keeps the same base for the log, and it keeps the same base for the exponential part. So it used to be m to a power, now it's just m. So bring the exponent out front and multiply it, and this parallels the exponential rules of having something like x squared raised to the third power. When you have a power raised to a power, you multiply them, and this is showing multiplication of the exponent and the logarithm. So now we're going to look at some of the examples where we're applying those properties. And one of the most common examples is to have, using the properties of logarithm, to write a single log as a sum or difference of multiple logarithms. So the first thing I'm going to recognize on this one is that I have a natural log of 8 times y, which means I could split that up as the natural log of 8 plus the natural log of y. So I'm using the first property where I show you that when two things are being multiplied, you can break it up as two different logarithms being added together. Now there's actually a little bit more I can do on this one, because I actually, hopefully recognize that 8 is the same as 2 to the third power. So look for any of the common exponents and powers of like 2s, 3s, and 5s. They like to use those a lot to see if you can break a number down, because then we can use that third property I give you guys to bring the exponent out in front of the expression. So now I have 3 times the natural log of 2 plus the natural log of y. And that should be all they want for us to type in our answers on this. Now we're going to do one of the examples where we're working backwards with the properties. This time we're going to take the multiple separate logarithms that we have and combine them into a single logarithm for our answer. The first thing you should do when you're working backwards on these is to bring the exponents up to the power spot again. So whenever you see a number out front being multiplied, that's them using the power property. So I'm just undoing that process. I'm bringing it back up to into the exponent spot. And then I also had a number 7 out front of the second logarithm. So I'm going to do the same thing. It's still going to be natural log of z. I'm not changing the base or anything, but I'm bringing the 7 back up to the exponent spot. So when you're working backwards, try and take care of the powers first, and then do any of the adding or subtracting steps. So since this is addition, I know that I can make this a single logarithm with the two pieces inside the logs being multiplied together. So x squared times z to the 7th. And you'll want to follow that basic sequence whenever you're going from multiple logs into a single log, do the powers and then do the adding or subtracting. And the other way around, you usually want to do the adding and subtracting and then bring the powers out front. So my answer should just be the natural log of x raised to the 2nd times z raised to the 7th. So now I have another property I need to show you guys. And this one says that whenever you have a logarithm, and it doesn't matter what the base is, and it doesn't matter what you're taking the log of, you can change this into two separate logarithms using whatever base you want. And that's why this is called the change of base formula. So most commonly, we use either the base 10 or the base e examples because that's what our calculators can compute. And the idea is that you pick whatever base you want, that'll be the a value. Whatever you were taking the logarithm of goes on the top, and whatever the base of the original logarithm was, that's what you're taking the log of in the bottom. So the base goes in the bottom, what you were taking log of goes on top, and you pick whatever base you want for the two new logarithms, but you have to use the same one. So usually we use 10 for both of those spots. Sometimes it's also useful to use e, and then we call it natural log instead. So this is useful for changing a logarithm that might have a base 2, 3, or 4 into a base 10 or a base e1, and that's especially useful so that we can compute them with our calculators. Now here's an example where I will use the change of base formula and plug this into my calculator. So the problem here is that the logarithm they gave us has base 6, and if you're using the TI-30XS calculator that I recommended, that one only does logs and natural logs. It can't evaluate other bases. So what I'm going to do is apply the change of base formula and write this as log, and I'm going to use base 10 in this example, of 70, whatever you were taking log of goes on top, over log, and I'm still using base 10 because that's what I'm choosing for the top. You have to use the same base in both spots, of 6. So the base of the logarithm goes on the bottom, whatever you were taking log of goes on top. And now, since both of these are log base 10s, I can compute each of these separately in my calculator. So at this point, you just need to type in log of 70 and then divide that by log of 6 in your calculator. Be careful about parentheses use. Make sure you close the parentheses after you hit log of 70 so that it knows that you're dividing that whole expression log of 70 by log of 6. And the directions ask us to round this to 4 decimal places. So for my example, I've got 2.37113, and the fifth number being a 3 means I round down and keep this as a 1 for my answer choice. So choose whichever base you want, but most of the time you're going to want to use base 10. Sometimes you might want to use base E, and then just plug these into your calculator. Now, this one, you should actually already be able to approach this, but I was afraid that there's a small trick in it that might catch you guys. So what I'm going to set up on this is trying to write it using only common logarithms, which means we need to change everything to log base 10. So my answer would be log base 10 of x plus y. I'm using the change of base formula again to change this into a base 10 log, divided by log of 1 over 43. Okay, so technically this is correct, and this is fine. We've changed this into common logarithms. But what I wanted you guys to remember was that 1 over 43, you might want to think of that as 43 to the negative 1 power. Because then it lets us simplify this a little bit more and get rid of the fractions inside of there. So don't forget, negative exponents give you the reciprocal, so that then we don't have any fractions left in our answer. Well, one of our properties with logarithms, though, allows us to take the exponent and bring that out front. So I can actually rewrite this as log of x plus y over negative log of 43. Now, for typing our answer, we don't usually like having the negative in the denominator like that. The most common thing to do with it is to just take it and then bring it out in front of the entire fraction. So I'm going to write this as negative, and then using parentheses on top, log of x plus y divided by log of 43. You'll notice I used a lot of parentheses just to make sure that I was getting things like both x plus y being inside of the logarithm, and to make sure that I have this whole thing in the numerator over the denominator of log of 43. And the last example I want to help you guys out with, they are asking us to take a log base 8 of x and transform this into a natural log graph, which means I need to use the change of base formula to go from a log base 8 to a log with a base of e, because that's what ln represents. So my change of base formula is going to make this ln of x divided by ln of 8. And here's where this gets a little bit tricky, because now I have the natural log of x function, which is what they asked me to identify, but it's being divided by the number natural log of 8, which is actually a constant. So what might be useful is to type in 1 divided by natural log of 8 into your calculator and think of it as that number times natural log of x. Well, 1 divided by natural log of 8 is approximately 0.48, and it keeps going on, 0.8983, but we're just going to be rounding this to the nearest hundredth, so this should be fine for right now. So it's that times the natural log of x. By writing it in this form, it's a little bit easier to see that I have the natural log of x function, and I am applying a vertical stretch or compression. In this case, the MATLAB assignment likes to call those shrinks when it is making the height shorter. So this one is vertically shrinking the graph by a factor of 0.48. That's from those transformation rules that if you multiply the function by a number bigger than 1, it stretches it. By a number between 0 and 1, it shrinks the graph down. And the reflections would have come in if there had been a negative sign attached to this as well. Now the second part of the question is going to ask us which graph matches 0.48 times natural log of x. So first you'll want to remember what the natural log of x graph looks like. And it has one of these two approximate shapes. This is what would happen if you were reflecting it about the y-axis. And this is what would happen if you were reflecting it about the x-axis. But we don't have any reflections going on. So I'm going to ignore choice C and choice D in this case. And it's also useful to remember in the last section, we talked about what the normal log and natural log graphs look like. Well, choice B appears to be what would happen if the graph was being shifted to the left, because now we're crossing some of our asymptote values that we're not supposed to hit. Since I don't have any kind of a horizontal shift, there's nothing being added or subtracted from the x value, my answer has to be the choice A. That's the one that seems to be showing the same asymptotes, the same basic shape of log. It's just been shrunk down a little bit vertically. And so that's going to be all for the notes. I hope that'll help you guys with the assignments. Thank you.